So take a look of the new circuit. Okay, and the same problem. What is the response of the circuit? And then you have the same equation, but your voltage now is AC. Okay, or your source is now AC. Okay, if you can remember, this is your equation, right? So this is the if you cancel, if you have the equations 1 and 2 and then derivation of 1 and then remove I2 using those equations, and you will have this these equations here, equation that you will be using. Now this time, what if the voltage is AC? Okay, uh, meaning you have a Vm sine Wt plus theta V. Okay, or yeah, that's Vm. No, so everything will change because here this becomes Vm sine Wt plus theta V. Now, if you remember in your ODE class, how do you call this? This is not anymore a ordinary differential equation. It is what? Okay, it's not ordinary. Okay, so because you have sine, it's a cosine value, and it would be difficult for you to manually solve it using differential equation, no, analysis, no. So you need to do some other way of doing it, no. So and then you will see that the current I1 that we are looking for to understand the response of the circuit or the behavior of the circuit is actually okay expressed by this particular solution. And you will see that if you replace this one with the V, the actual V in AC value, so you will have that differential equation, which very it's very complicated, no. And and this is in time domain analysis. That is why we use the Laplace, no, or Laplace, okay, Laplace transform, okay, for um, transforming the circuit or transforming the analysis into frequency domain, such that it would be easier to solve this or to analyze the circuit or any system that follows first or second or even nth order differential equation. Okay, but in this case, it's not a simple ODE because of the presence of the cosine and sine. Okay, this will be we are now converging into the use of Pacer algebra as well as the Laplace transform. Okay, so we are combining. So these things are very important. Okay, so especially if you want to design system, okay, and want to simulate things, so it would be better if you will understand, no, so the use of Laplace, Pacer, and so on. Okay. Okay, so we cannot use any more time domain. So a very simple circuit like this, it will take you a lot of time to analyze. Okay, but if we use other means like the one I said, Laplace plus Pacer, then it would be easier to solve things, and you can automate that one using numerical methods in um, numerical methods. Okay, because it's simply algebra, no. So Pacer algebra is algebra, and you can use linear programs, no, to do things like that, instead of doing derivative, no. So we use numerical methods, especially for complicated systems. Okay, time check, 10 minutes. Okay, now here you can see sorry, you can see here an example. um, okay, an example of a simple RL circuit in AC form. How do you hide this? Sorry, hide. Okay. Um, so you have here, you see, you have the voltage. Okay, you have the voltage here, in AC, and then the current in AC. And you can see that Vm is the magnitude of your V, and then you have the sine wave. So actually this one here, okay, if you can remember, that's the behavior of your Vm. Okay, why is it VOE to the ST? But why is it that's our particular solution? Because we have the first order circuit, no? So but if it is second order, then that would be V equal to VOE to the S1T uh, plus V, let's say BO prime, BO double prime. But prime, you might think that, so you can use uh, other constant, will be A e to the S1T, B e to the S2T, and then that would be e to the j theta. You can remember that this one we can express with an exponent, exponential form. Okay, can you recall? So actually this one is Vm angle theta, okay, in a phasor diagram. Okay, so but we convert that one into exponential form. Now this one here is where the exponential is very important, and then you see the complex number j. Okay, so this is very important. Okay, now here we are applying the phasor algebra so that we can simplify the steps of solving differential equations. Okay, you may use other analytical methods, homogeneous, whatever. Okay, but here we apply phasor algebra so that it will be easier to solve the differential equation. Okay, so okay, I think I have made a mistake here. It should be theta. And okay, so from the circuit here, summation of voltage is equal to 0, and this one here is the V. Okay, and this one here is the VL, and then this one here is the VR. Okay, I hope you will not question this thing, no? Okay, so and then this one is theta, should be theta. Okay, and for your current, actually our goal is to get the current. Okay, but this is the particular solution, meaning we don't know yet the I0, and then you have the S. We don't know S also, no? So if you perform this method, just actually you have the particular solution here. That's our particular. So you can substitute this one with the I, with the I0 e to the st plus L d over dt, I, which is I0 e to the st, e to the, sorry, I think I forgot here, e to the jp, jp is equal to v o e to the st, e to the theta. Okay, now because it's easier to differentiate exponents, so that's why our form here is exponential form. Okay, so you just arrange the equation, and um, you will see that if you derive this, uh, actually, you can uh, just a moment. 5 minutes na lang guys. Okay. So yeah, we have, yeah, if you continue this one, okay, we don't have a derivative here, so very simple. We are IO e to the st, e to the jp, then plus L, and if you take the derivative of this one in terms of time, so dt man ni siya, so we only have to derive this, and then the rest are coefficient. This one here and this one here are coefficient, so we can write IO e to the jp, and then derivative of this one is s e to the st is equal to um, v0 e to the st e to the theta t. Now if you can cancel something, you can actually cancel this one here. And then what else? Okay, I think nothing more, but you can differentiate e to the, you can separate e to the p, then r plus ls. I hope you can.
LS, sir.
I bring the IOE to the JP outside, and you got R remaining on the first term, LS to the second term, and then it's equal to V0 e to the theta. Okay, sorry, I forgot the J, and I think this is not T. I think I made a confusion. J theta. Okay, so I think I made a mistake. J theta. Okay, and then our goal is to find the I of 0. Okay, so para complete, we can express then the I. So I of 0, um, actually you can write e to the j p is equal to VO e to the j theta divided by r plus ls. Okay, so um, you can actually bring, so you can use this one here. So your final answer should be uh, I of 0 gt. So you have VO e to the j theta over r plus ls, and you have uh, e to the sorry, should be e to the j. Okay, and then if you convert this one to phasor, you have VO angle theta divided by r plus ls angle p, or you can express this one as VO angle theta minus p, okay, divided by r plus ls. Now r plus ls is actually the impedance, okay, so VO over the impedance V. Okay, now we will define this one ls later on. So that's it. So that's your current. I is equal to you can have this as your final answer. So but what we're doing here is to show to you the the steps, no, how to analyze a circuit easier. So this one is very simple, RL circuit. Now if you have more complicated circuit, then you can use the phasor algebra as well as the Laplace later on. Okay, so especially for um, RLC.